Swayam Prabha. Digital India. Educated India.
This lecture, I would speak about some motivation to look for such nonlinear systems, and then I would discuss some properties of nonlinear harvesters. Then I would also speak about subharmonic solutions. I told you that in nonlinear system we can change the response frequency with respect to the input frequency. So we have one signal from the ambient vibration with a given frequency, but because our device is nonlinear, we can have different frequency in the output, and then this is also in subharmonic solution. And then I would tell about stochastic bifurcation. So I gave some introduction to you for linear stochastic systems, but in nonlinear stochastic systems you have some other phenomena, and one phenomenon is also called resonance, and this is stochastic resonance. So in such way you can expect that the output or response of a voltage response, it is more it's more regular than the input. Yeah. So this is interesting point. But the nonlinear system can make more regular the signal, and this is also some feature of nonlinear system. And there are some number of resonances with stochastic resonances, and also stochastic bifurcations. Stochastic bifurcations are they are happening if you have some switch between solutions. And then you have some concept of nonlinear energy sink. And so the nonlinear energy sink is a concept that you can direct the energy in some way. And then there is another field which is coupled harvesters and synchronization. So the coupled harvester can be used because we know that there is some miniaturization of the system, and sometimes we need to design a harvester for more energy. So one of the possibility is to just couple a few harvesters and to get better response, and then synchronization could be important. I'm not telling that this is the main topic because sometimes you need to do some work with power electronics, and power electronics is also useful for us. However, synchronization phenomenon is very similar to resonance. So you have two oscillators, and these two oscillators could resonate, and this is synchronization. So there is some added value that the synchronized oscillators are responding much better than just individual, or the sum of the individual resonators or oscillators. So I would end up with conclusions, and this is the program for 2 hours. Yeah, so in the middle we can make a break. I would like also to show you the campus and the city. So this is the city Lublin. City Lublin is somewhere located in the eastern part of Poland. It is the largest city in this part of Poland. So this is capital of a region, and we have about 400,000 people in the city. So here, if you move down, there is a building of mechanical engineering. Yeah, so this is like a faculty of mechanical engineering building. Behind this building, there is another one with laboratory, and in this picture you can see the rector office. Yeah, so this is a rector office, and that one is the same as this one building, but we have some special illumination at night. Yeah, so nice illumination for this building. So we have a few faculties at our university, but we used to have some similar number of students like you have here, about 10,000, but recently the number is decreasing. So I think for the time being we have probably around 8 or 7,000 students in our university. So then I would go to the presentation. This is again some introduction to energy harvesting. You see that we are not going to have a large amount of energy. So we are thinking about small sensors, powering small sensors or some small electronic devices, and the most useful device is composed of piezoelectric. It could be also electromagnetic. However, there is not such a possibility of scaling of electromagnetic. So you need more space, and one of the effectiveness factor is that you relate the output power to the volume. So this is the good ratio for piezoelectric. For electromagnetic, it is a little bit lower. So you need larger volume to get transaction. And power electronics is important, but I would prepare you some maybe some material about electronics, how to transform, how to rectify the voltage output, and how to connect different voltage outputs just to have stable voltage, how to stabilize this output. So this is power electronics, and we are not going to discuss today with power electronics, but there is some progress also in power electronics, and I told you that there is such a maximum power tracking. So there is such a method for electromagnetic harvesters, and they can be also used for coupled systems. So if we go further, there is some application and motivation to derive to design some good harvesters, and you can see that in different branches you can apply these devices. So there are still some challenges, and one of the challenges is durability. So it is difficult to study durability because we have so many devices. You know that durability is less for piezoelectric because you know that it is a brittle material. So for that reason we are using some some multi-fiber composite, and you would learn at laboratory that this multi-fiber composite is more flexible, and we have to select the material. And so yesterday you had such a presentation on materials. So this is very important, but not only to the smart material, and including also piezoelectric, but also the substrate should be properly selected to have a proper stiffness and also the properties like magnetic properties, because sometimes we are using electromagnetic energy harvesting, and this is important. That we have some additional substrates which are not ferromagnets. So we should select aluminium or some other material. We should look carefully to the material, and we have some other challenges like energy storage. So energy storage is another point, because we also design our harvesters. This is a little bit related with the energy storage, and management is more related to power electronics, because we need to transform the voltage for the best is to have a constant voltage, but we have variable voltage. Yeah, so rectifier is sometimes not enough because it is losing some energy. So it is important to improve, and also energy storage. There are some concepts of supercapacitor, not only traditional batteries, and this is important issue. But today I would speak about the frequency. So the frequency is also one of the challenges with optimal resonance frequency. So the nonlinear system, sometimes it is we are telling that we can work off resonance, but this is only half of true, because in nonlinear systems we have more solutions. So we could have some other resonances. So we have more resonances than in the linear system, because in the linear system we have only one solution. Yeah, so only one resonance. And if we are telling that we want to work off resonance, we are thinking about the linear resonance. So in that system, nonlinear system, we have some more resonances. I will show you that aspect. So I told you that the concept of piezoelectric energy harvesters appeared in early 2000 years. So there were some concepts. However, people were disappointed because in that system you should work in the resonance area. I mean mechanical resonance, because we need to have some kind of transducer, and transducer is composed of elastic component and also multi-physics field or multi-field element, which could be piezoelectric. Piezoelectric is sensitive to at least two fields. One field, because there are some more, but one field is electric, and then it is stress, mechanical stress. There is one more is like temperature. So you can see that this would be also important sometimes, but we are not going to speak about the temperature. So we have now we have two fields. One is electrical, and the second is stress. So during the elastic deformation, there would be some reconfiguration of the internal structure of a piezoelectric, and this would give some change in the polarization. So as we discussed in the previous meetings, this piezoelectric should be initially polarized. In such way, we have some region of work that we have some small deviation of polarization, but this is enough to have a voltage output. This is enough to have voltage output, and you have in fact the substrate, which could be like metallic beam, cantilever beam, and this is covered by piezoelectric, but you have also some electrodes on the top of this piezoelectric layer, and maybe on the bottom is like could be metallic substrate, could work like electrode, the second electrode. So you, in such way, you have deformation inside the material of a piezoelectric, and this is elongation or contraction in such way. There could be some effect on the dipole. Dipole properties inside the material, and for that reason we would have electromotive force inside the capacitor, which is composed of two electrodes, and these electrodes are connected to the electrical circuit. So here you can see these electrodes and the material inside. So you have some polarization. So the polarization of the material, and you have also electrical field, which is E. So you can see the polarization vector, which is coming from the material, and this is some kind of electrical field, because electrical field is coming from the charge which is located in the electrodes. So we have some play of the electrical fields from the electrodes, and also the polarization from the material. So the polarization of a material is changing because we have some applied force, and when there is elongation of the material, deformation of material is changing polarization, and because the polarization is changing, when we have some effect on the electrode. The electrode is connected. The electrodes are connected through the resistor, and there is a current in the system. So this would be variable voltage on the resistor. So this is the working principle for the piezoelectric. But you remember that it should be initially polarized, because otherwise, if you have some random orientation of polarization, then it would be difficult to operate, and there would be some effect, but very poor. It would be very poor effect. So I think that some researchers are still working with some small effects, some biological alternative for piezoelectric, and this is, or maybe some foil, which is easy to convert. The ions can be converted quite easily in the foil, the piezoelectric foil, or some natural systems, biological alternative. Yeah, but these have very poor performance, and that one which is prepared, especially industrial products with proper polarization, has very good response. So I told you initially that there was such a paper on nonlinear effects. The first paper which described the broadband response of harvester was published in 2009 by the group of Inman, and Artur is now famous professor, but he was a student of Professor Inman. So both are very well known in the field. This was this paper discussed some simple system, which you probably know from many many other applications. But this is the beam which can be excited. The beam is clamped to the frame, and this is excited horizontally. It could be vertically, but then you need to rotate the system. But this is horizontally excited. So the vertical position of a beam has some equilibrium of oscillation, like the shape would be vertical, exactly vertical, and around this shape the beam would oscillate. So you can see, but telling about the shapes, it is different story, because you can imagine that for modeling we need to have some continuous body theory, and continuous mechanics. So it is possible, however, to look for the first mode, because we are telling that first mode is if you have only the deflection to left and right, and this is the curvature is the same along the beam. So if it is deflected to the right, all the points have the similar curvature, but not exactly the same. The piezoelectric is placed in the beginning of the beam where it is clamped, because otherwise it would be some back effect, which is not good for us, because there would be if we have the piezoelectric along the whole beam, there would be tendency to have the same curvature in every point of the beam, and this is some work which should be done in mechanical structure. We would like to avoid any additional work in the mechanical structure, because it is waste of energy. We would like to transform the energy to the electrical form. So we place the piezoelectric at the beginning of the beam. Yeah, so here, somewhere here, and this is the electrical circuit is attached to the electrodes to the piezoelectric placed here, and these researchers, this was like a short paper, and they discussed the effects without placing additional magnets, which destabilize the vertical position of the beam, with the original structure without magnets. So if you have original structure without magnets, you have one equilibrium point, which is related to the vertical shape of the beam. And if you assume, because there was such an assumption, that the beam is ferromagnetic. For ferromagnetic beam, you have some attraction to the magnets, so to the right-hand side or left-hand side magnets. And when you have two equilibria, and you can find some small oscillations around one equilibrium and the other equilibrium, or if you have larger excitation. So larger excitation means usually larger amplitude, but it is also related to the frequency, because if we are closer to the natural frequency of the beam of this first mode oscillation, we can lower a little bit the amplitude because this would be very efficient. So they found that if you look to the system without magnets, this is like a linear system, and you can see that there is there is a maximum point somewhere here for the frequencies around 7, and for the system with magnets, you have a much larger response, and this is like a broadband. So they called this broadband effect. Broadband effect, but you needn't be exactly at this point, but you can work in some other place. So this was called broadband, but was not explained in this paper. And simultaneously there was another paper by Italian people. I told you yesterday about that, and it was a similar structure, a vertical structure of a beam. However, beam was excited in a different way, and there was an assumption of a stochastic excitation. Yeah, so there was an experimental part, and the vertical position of the beam was destabilized by some repulsive magnets. Two repulsive magnets just placed at the end of the beam and on the frame. So you could see that there is also left and right stable position, and if the increase length, so the gap between the magnets is large, then there was no effect. So practically no effect, and you have some parabolic shape of the potential with single equilibrium point. And if you have smaller distance, then it was just like there was such a creation of these two minima. Minima is signaling that there are two equilibria, and if you have some energy in the system, there would be oscillation around this point or oscillation around that point. So you can see that there are two solutions because these are different solutions. So in the linear system, there is only one solution because you can think this is like a potential energy, but if you are above the line, the bottom line, you see that there is such a energy which could be the energy is constant and the potential energy is minimum. And because the energy is conserved, the rest of energy is kinetic energy. So if you are you think that there could be some oscillation with turning points. So it is going to the above the line. For some levels of energy, you have larger and larger amplitude of oscillation. And if you have some random excitation, you can imagine this random excitation, but this is not like a periodic, but this is very periodic. Is like a regular feeding of the system, but this is in energy. But this is like such a stochastic excitation is influencing the level of energy. The level of energy. So if you have some special level of energy and the barrier is relatively low, you could have large amplitude oscillation if you are above this barrier. And this was found. So this is like an easy effect, but it was found that for some noise level, the output, this is like power output is here, yeah. The output power is increasing considerably. Yeah. So and this is in the literature. This is also called like a stochastic resonance, but it is not a classical stochastic resonance where you have two signals, both like periodic and stochastic excitation simultaneously, but this is coherence, stochastic coherence resonance. So stochastic coherence resonance was studied also for some biological reasons. And so it's a potential just to inform that you have some destabilization of equilibrium. The equilibrium is not in the vertical position because there is some x, and I should tell that x is the position of a tip point. It's a tip point position. So sometimes it's not it's not tip point because according to this figure you see that this is some laser. So the x is some point which is close to the end, and this is measured by laser. Yeah. But in simulations, we usually assume that this is like a tip point. Yeah. However, here it is even written. If you look carefully, that this is written x. Yeah. So x is placed here, and for each x, the potential energy of a beam is calculated.
So, sir, what is the significance of this cantilever energy over the power, piezoelectric power output? Like in main position, the power output is zero because it is in stable center position.
Yeah.
There is no stress. So when it is in extreme position, it is producing the stress and producing power output, like the beam.
If it's not moving, then there is no power output, so it should move. Yeah, it should move. Yeah, and here on this picture, you can discuss only the equilibria. So the equilibrium is here, and this is like unstable on the barrier. Yeah.
So what is the significance of this two? What about this?
For piezoelectric, so I mean that the piezoelectric can so this is a good question, but I would come to the question later. So it was written in the equations, for example, or the piezoelectric itself. It is producing some voltage once there is some deformation. Yeah, and you need to have larger deformation. So the larger deformation is related with larger amplitude, because otherwise there is some decay of the voltage. So if you bend the beam, but it is connected with the electrical circuit, then the charge would flow around the circuit just to balance the polarization of a piezoelectric, and finally it would stop. So it would be it is the effect that the charge would be also change on the electrodes and to balance the polarization of a piezoelectric. And if it is not moving, but it's bent but not moving, then because we have electrical circuit, it is not open circuit, and the charge can flow. It would be the decay. So the charge would be balanced on the piezoelectric and the electrodes, and there would be no voltage on the resistor, electrical resistor. So, but if we are if the system is moving, then you have a continuous change of a polarization, and then you have a flow of a current, continuous flow, but it is alternative current. it's alternative current. Yeah. So we need some good. We need some large amplitude. And a large amplitude, you can see that it is possible to get such a large amplitude from the potential, because if you have such a parabolic, parabolic picture, you can, it's like a parabolic potential. You can see that you have some energy, because this is like a potential energy. So if you have the point on the curve, you can interpret this point that there is the potential is just equal as the energy level. The potential is energy. Potential energy is equal to energy level, to total energy level. So there is no motion, because all the energy is in the deflection. So the potential in the only the energy is like only potential energy, and if you move to the middle, you can see that the potential energy is in the minimum, but the total energy is conserved somehow in the system in a short time. So you can tell that this energy is transferred to kinetic energy. So there is like a motion. On the edges there is a turning point. So you cannot cross the potential barrier only if you are above this with a level of energy, and excitation is adding some. By excitation, you add some energy to the system, and if you add the energy in the periodic way, you have some plus and minus. This is somehow is difficult to estimate what is the current energy level. However, if you have some stochastic, then the most important effect is that the stochastic is depending on the intensity, but you excite in the stochastic way, and you can expect that the main effect is just increasing the energy level in the system. Yeah. So if you have some noise intensity, and this is higher and higher, you can pass through the potential barrier. And this was checked in the next paper. But if these are just levels of noise. So if you have some large level of noise, then you pass through the potential barrier, and this is in terms. So you see that horizontal is like a size of this length of a gap between the magnets in the system. Yeah. So this is the. This is some kind of design for experiment, yeah. But they wanted to check what is the response against stochastic excitation. I told you before that there are two limits, because in the nature ambient vibrations are variable, and there are two limits that one can assume in the laboratory that you have periodic excitation, or you can assume that this is like a purely stochastic excitation. Yes. So two limits, two extreme limits, because you can imagine that there is such an excitation with several frequencies, and maybe if you for example, if you place your harvester to some other mechanical system, which is like a motor, and you want to use this as a damper, this is some good idea. But you dump, and you simultaneously you dump vibration, and simultaneously you harvest energy. Then you can find that there would be more frequencies. Not just one, and this is some problem, and so people are also studying this, but not so many papers on that. So usually we are in the laboratory or some simulation. We want to be more general, and we are telling about sweeping of frequencies. If we have harmonic excitation, we are telling what is the response for given frequency. And stochastic could be also also come together with some periodic components, and I will show you such example later. This is some explanation to that works, and I just want to tell that this was a paper which appeared in the same year, like 2009, the same year as the other paper with American group, Italian group, and you see that there was such a huge jump of a response in terms of power here, and this is in terms of mechanical amplitude. So in terms of mechanical amplitude and in terms of power, and the reason for such jump is also that if we have very small amplitudes, when nonlinear effect is not working. If we have larger amplitude, the nonlinear effect is more important, and for that I would tell that this is some kind of regularization. So it is the input is like random, but the output has some natural. This is not the natural, but characteristic frequency for the large amplitude. So there is some additional resonance, which is so the energy is enough to jump jump to another solution to overcome the potential barrier, and when there is such a tendency that this oscillation becomes maybe here, but the oscillation above the potential barrier becomes regular, periodic, more periodic than the input, and this is called also stochastic coherence resonance, and I wanted to tell that this is present in biological systems like in the brain. Sometimes you add some special there is some oscillation in neurons, and if you take some medical drugs, then you sometimes increase the level. So you have not enough oscillation, and you increase the level when your brain is starting to work better. It's improving. If you have some because you excite by some noise, by some medical treatment, even some chemicals. You take some chemicals but this is some kind of analogy. So because the neurons they also show some kind of stochastic coherence resonance. So I that, and we go further. So I can tell you that there were some different effects discussed by DACAC, which was like 2014 review paper. It was one of the first review paper on these different effects for the influence on the energy harvesting. So they discussed some inclination of the resonance curve. So you can have a softening effect in terms of the force and restore force and the displacement. So softening effect is with respect to the linear. It's a linear. It's like a straight line. Characteristic of the restore force for the spring, and this is the hardening effect and softening effect and hardening effect. Softening effect is moving your resonance curve to be slightly inclined, but it could be like extreme effect like that. You have inclination to the lower frequencies, and for the hardening effect, you have inclination to the higher frequencies of the resonance curve. And there is another effect that there are two solutions. If you have such an extreme inclined system, and this inclination of hardening could also be helped by some stoppers. If you have stoppers, then this is very hard to just you have impact, but you cannot move through some points, and when this is hardening effect, and for hardening effect you have two solutions, which is above the line is like a large. Because here you have a frequency and here you have the amplitude. So you have two solutions with small amplitude of response and a large amplitude of response. And these are called resonant solutions and resonant solution and non-resonant solution. So these two solutions can be present in nonlinear system. It's not only that you have the two solutions for the two potentials, two minima of potentials, and also the third solution which is coming through the potential barrier, but you can also have single resonance and resonant and non-resonant solution. So this is one effect that that the inclination is present. The two solutions is another effect. But if you measure the length of a good response, it is also extended. However, at the end there would be two solutions. Yeah, but it is some drawback. But this solution with a low response amplitude is also present. So you can check how robust it is the solution, but then you need to calculate the basings of attraction. So in basings of attraction is telling you which initial conditions are leading to given solution. Well, this is the set of initial conditions, basings of attraction. And if the solution has larger basin of attraction, then it is more robust. So one can look for that, which solution is more robust, but it is not so easy to find just from this figure, yeah, because you need some additional study. And also you can imagine that if your frequency is changing slowly, you can follow this path, the upper curve, and if the frequency is sweeping down, then it could take another curve with non-resonant solution. So there would be some hysteretic effect with this sweeping. So this is a dynamic hysteresis. It's called dynamic hysteresis for nonlinear resonance. So it is also present in nonlinear systems. This was discussed in this paper. Yeah. Yeah.
That is like a deformation.
Yeah, it is here you have some deformation. This is displacement. And this is the restore force. Restore force, yeah. So this is like a force which is, you elongate the spring, and the spring is acting in the other way. Yeah, so this is like a spring force, which is going back.
Here the softening region is below the natural, like
this is like a softening effect, and this is hardening effect.
Above one.
Yeah.
That line is softening effect.
This is only yeah, you are right, but this is not it is just beginning of this curve, and this is not continued. It could be that this is not the full story. It's only it's only for some range of displacement or deformation. So this is not the whole range of deformation or displacement which is plotted here. Yeah. So I just plotted this curve by myself to explain this inclination, which was assumed by this paper, Takak, Masana, yeah. So this is some simple explanation. But if you have such different cases, you can observe different forms in the resonance. But inclination of the resonance is also some information. If you find some inclination in the resonance, you have some information that nonlinear effect is there. Yeah. It's in the system. The nonlinear effect is in the system. If there is some inclination in the resonance. Yeah, so this is also possible to discuss in such way. And here I think it's the third one. I told you about these subharmonic solutions. So subharmonic solutions were investigated in 2017 by the French group, and they have one. This is the first paper of this group. This was followed by some maybe two others, and in the first paper they studied electromagnetic system. In the next, they studied piezoelectric, but it is the same phenomenon. I told you that the size could be a little bit different because. But I think in the laboratory we also have similar sizes for electromagnetic and piezoelectric, because these laboratory studies are not optimized for application. But sometimes for application you can make smaller size with piezoelectric comparing to electromagnetic. And I would tell you what is the system here. The system was here. Yeah, it is not so easy to follow, but here is the sample. The sample is based on. This is the also here it's presented. There is a special rod. There is a special rod with a magnet, and it is going in this way just to be included to the coil, inside the coil, and this is changing the magnetic flux inside the coil. Yeah, if you have such a motion. But here there are some other beams, two beams, which are pre-stressed, backward beams, and these backward beams are giving you, two stable positions of the rod on the left and on the right, and so you have you have bistable potential with two equilibria, like it was studied in the previous papers. But you can by this system, this is electromagnetic system with single coil, and you found some branches. If you look here, there is some. This is the displacement. This is the displacement. So the displacement is coming. This is the first. This is the solution, the leading solution, which you think that you can find for some the basic frequency, which is given to the system by excitation, because the system was excited periodically, like before on the frame, and here there are some other branches. Yeah, so there are some. This is the branch which is called subharmonic 3, and this is subharmonic 5, and this is the harmonic. This is also first harmonic. Yeah, so it's not harmonic response, but it is called first harmonic. This is first harmonic, and this is like subharmonic 3, subharmonic 5. And this is non-resonance. So this is like a resonance here. This is non-resonance, this is resonance solution, and this is non-resonance solution. However, if you pass the resonance, there is another kind of resonance, which is appearing with second branch and the third branch. So it was interesting. If you look to the power output, the lower figure is the power output with correspondence to the amplitude. You have a larger response in amplitude. You have also voltage output, which is a little bit proportional because this is linear. The electrical system is linear, and however here this is power output. So this is voltage square. Voltage square. So if you have relatively small voltage, then it is unfortunately smaller, even smaller. But if you have relatively large voltage, then this is even higher. Yeah. So it is such a tendency. So I think that this one it is very important, telling you that not only these effects which were discussed by Dakak in the previous review paper. The review paper was 2014. They haven't discussed such different, solutions, but the solutions are just different in the frequency, because you see that this is the frequency is single frequency, and with some multiple frequency responses. Subharmonic. So you think in subharmonic you mean that there is some, for example, subharmonic 3, meaning that you have 3 pulsation of excitation and 1 response of a system. So in voltage there is the 1 response after 3 pulsations. So you can accumulate energy during during excitation. So you can pass through the potential barrier, but accumulating 3 pulsations. So this is possible only for the harmonic excitation and nonlinear system. Yeah. So this is interesting, and we have studied more carefully these effects, and we also found such a chaotic solution. The chaotic solution somewhere here. You see many points. The branches. So this is the same. However, here you have some transient double well potential, which is sketched, and you have which is working like original Ertug Hickman paper, but you see that there is one branch. The one branch is it is response with the same frequency as leading frequency is like excitation frequency, and of course this is a large displacement or large amplitude response. So you have also some manifestation of nonlinearity. The response is more complex, and this is not exactly harmonic. Yeah, so there are some other harmonics. However, the leading frequency is the same as the excitation frequency, and in the other branches, the leading frequency of the response it seems to be lower than the frequency here. So the period of response would be higher, and for chaotic it is like very large, because practically it's large, but in theory you never go back to the same point. In chaotic solution. Yeah, so this is some extreme limit of that. And I just want to finish this part with this studies of stochastic of subharmonic solutions, but I want to tell that we also studied some switch between solutions. So you see that we start from the solution in the system which was not excited by noise, but we added some noise to the system. This is the same system as studied before. So the equation was like I discussed yesterday, but there is some difference to the restored force. Restored force is now for bistable system. So you have different potential, mechanical potential, and when there is a potential barrier, you overcome the potential barrier if you have enough noise. But simultaneously, you can also switch between solutions. So you can look, for example, calculating the frequency, which is and checking what is the leading frequency by Fourier transform. And then by Fourier transform, you see that if you have zero noise, then you have the output is that this is like a peak line, and there is another dust line. Dust line is the excitation frequency, and this is the response, the Fourier transform of the response. And you increase the noise when something is happening here, but it is not very large, so you have still leading frequency like excitation frequency, and then you switch to large amplitude, because this is also measurement of the amplitude. In the Fourier transform, you have some response with you have information what is the output level with each frequency. So you can see that the response was small, but you can get larger response for some higher level of noise. So it's not only that the system has more energy and this is moving faster, but also this is some different way of accumulation of this energy by mechanical oscillator. So mechanical oscillator absorb energy just and to the motion with different frequency. And this is like a subharmonic solution. This is present only in some nonlinear system. And this was some probability distribution in this system of the voltage. Yeah, so this is some additional information, but maybe not such interesting.